All right. Well, good afternoon, everybody. Again, thanks for joining me for physics class today. Normally on Thursday, I know I try to want to do labs or some sort of demonstration, but with the short week this week, I wanted to do some review of what we had started before winter break, and that was Newton's laws. And we did a little bit of that earlier this week. Today, I wanted to go through a full-blown review packet with you here today. And the answer key I will post to this after class. I want you to go through this with me today. I'm going to ask you guys to kind of help me through some of the problems. So if I don't hear anybody trying to help me through a little bit, I'll try to coach you through to give me some direction. I want to make this one a little bit more interactive than we have in the last week or so. And so let's get started from there. Right, so hopefully you found in today's Schoology folder the review sheet. And again, this is all over Newton's laws, over the three Newton's laws that we had talked about so far in this unit. Newton's first law, the law of inertia. Motion at rest tends to stay at rest. Motion, an object in motion tends to stay in motion. That actually is what our first question is right here. When there's no net force in an object, what does the object do? If it is at rest, if there's no net force, it stays at rest. What if the object is moving? Right? Again, if there's no net force, an object in motion tends to stay in motion. What does that mean? It's also moving at that constant velocity. No net force means no change in acceleration, no change in velocity, rather. And what is this concept called? We call it inertia. And like I just mentioned, this was described by Newton's first law. Okay. Now, Newton's second law was F equals ma, force equals mass times acceleration. And to be more particular, that force was the net force. And that's why we would draw our free body diagrams. Right? We draw the free body diagrams to identify all the forces, and we can identify the net force. And we tended to do that in two orthogonal, two perpendicular directions, like the x and y axis. It makes our math much easier to do it that way. And finally, our third one then was the Newton's law of where equal and opposite forces, equal and opposite reactions. So if an object exerts a force on another object, the second object exerts an equal and opposite force back on the first. Really, it's the second one we're going to use the most, but they're all going to be tied up in here as we go through. So when we look at the second one, when there is a net force on an object, what happens as a result? It kind of goes back to Newton's second law, right? If there's a net force, that means there's going to be a net acceleration. What's acceleration? A change in velocity. I'm going to be very careful about that, a change in velocity. Remember, velocity is a vector. So if we want to change velocity, we're either going to change its magnitude, its speed, or we can change its direction. Both very important. Two ways to change velocity, two ways to cause an acceleration. So I do want to encourage you guys, pipe up. If you have questions as we go along, in a little bit, we'll go through some of the summary stuff. And then we'll go back in and we'll start doing some calculations. Newton's third law states that when an object A exerts a force on object B, again, this is just reviewing these Newton's three laws, object B exerts an equal and opposite force back on A. Opposite meaning opposite direction. What is the Newton's third law reaction force to the force of the earth pulling downward on you? Now, this is a common one that students get wrong. They'll say it's the floor pushing back on you. That's not the equal and opposite force, right? Because it has to be by the same two objects. If object A exerts a force on B, then the Newton's law force that we're talking about here is B exerting a force back on A. The floor isn't pulling you down. But the floor is responding to another part of it. But the equal and opposite force here is you pulling upward on the earth. Same two objects. When we're doing Newton's third law, Newton's force pairs, it's the same two objects that are always involved. When an apple sits on a table, the table exerts an upward force on the apple. What is Newton's third law reaction force to this? This is a trickier one. I want you to look at how the question is worded. When the apple sits on a table, the table exerts an upward force on the apple. So according to Newton's law, third law, what's the equal and opposite force here? Can somebody tell me? Either type it into the message box, public chat box, or speak up if you're connected with your audio. Oh, come on, guys. The apple exerts an equal and opposite force on the table. Excellent. Thank you, Mason. Exactly what I was looking for. Same two objects. Table exerts a net force on the apple, so the apple better exert a force on the table, and it's going the opposite direction, so we're going to say the apple pushes down on the table. Okay, that's when we're talking about action-reaction pairs. What is the name for the state of an object on which the net force is zero? So when something has no force, you're experiencing no force, we had a special word for that. I went over this one really quickly, but it's a common enough word I'm hoping somebody will remember. If you do remember, please, again, either speak it out or put it into our public chat. I'll wait a few seconds since I did not stress this one very much, and then I'll put the answer back up on the board. Yeah, this one I thought might be a little harder because I went over it so quickly. The term we used was equilibrium. Again, hopefully that's a word that makes sense and is, you've heard before. Equilibrium. Everything balances out. There's no net force. We're in a state of equilibrium. Now we're going to get into a couple of them that I really do want a little bit more engagement from you guys. And this is where we're going to start drawing a free body diagram. Drawing a free body diagram. So in this particular case, we have a block, and it's sitting on a ramp. The block is not sliding down the ramp. It is at rest because of friction. Who can tell me what forces we need to put on here? Yep, there's gravity. Excellent. That's one of them. Which direction does gravity point? Down. Very good. So I'm going to put the first force here. We're going to put gravity. We'll put an F with a little G on it, saying force of gravity. Are there any other forces acting on our block? Yes, a normal force. Normal force. Which direction should we draw the normal force here? You're warm. It's not simply up. What does the word normal mean in math class or geometry class? Yeah, kind of diagonally. I'm looking for something a little more specific. Perpendicular. Yes. It's perpendicular to the surface. It's normal to the surface. So I'm going to put an F with a little N for normal. Excellent, Riley. All right. Any more forces, or are we done? Well, if you look at this problem, it actually tells us that there's friction. So we need to put some friction in our diagram. Which direction should we put friction in? Can anybody tell me that? Yes, on the side, Ibrahim. Which direction, though? Can somebody kind of describe the direction for me? Downwards? Not quite. It's going to go a bit to the left. So when I draw the arrow like this, Parallel to the slope. That's what I'm looking for. Exactly. Exactly. So instead of this last little arrow I put here, right, friction's going to the left. Really want it parallel to the slope. Now, how did we know that friction was pointing up the slope and not down the slope? How did we know that? Yeah, it's not moving, right? So a little bit more. Yes, gravity wants to, I'm sorry, friction wants to slow down an object. So if an object's moving, friction wants to slow it down. But if an object's not moving, what does friction do? It's resisting the beginning of the motion. So if we take friction out of our picture here for a moment, if I said we have no friction, what would happen to our block? Would it just sit there on our, would it just sit there on the ramp, or would it move up or down? Right. It would slow. It would try to move down the ramp. So if that's the direction it wants to move without friction, friction's going to try to oppose that motion. That's how we know that friction's going upwards here. Another way we would know is when we looked at our problem. What did it say? It said that our object was at rest. Object was at rest. So there's no outside force. It's not sliding down the ramp. It's no outside forces. So we know when we add up all the forces in our object, they better add up to 0. And the only way we could do that, if we would have drawn our friction arrow the other direction, instead of drawing it up, if we would have drawn it down, right, we would have had a lot of net forces. Those 3 forces wouldn't have added up to 0. There's no way those 2 would have added up to 0. So that's another way I want you to be thinking about this sometimes. If we know there's no motion, then we know all the forces are canceling each other out. And that'll help you a little bit with the direction sometimes with friction. Good job, guys. Good job. Whoa. We get through all 7 of them, I thought. Yes. All right, next problem here. Draw a free body diagram for a car crashing into a brick wall. So what's the first thing we do? Just do a free body diagram. The very, very first thing I ask you to do when you draw a free body diagram, what is it that we do? We're going to draw a box. Okay. We're going to draw a box. So our box is going to be our car in this case. So let's write down, what are the forces acting on our car here? What are the forces acting on our car? First one should be really easy. What force acts on almost every problem we're going to do? Gravity and normal force. Excellent. So we're going to have a gravitational force. Gravity is always going to point down. Normal force is going to point perpendicular to our surface. Well, if the car is riding on a road, then that perpendicular surface is going to be pointing up. How about the wall? How do we put the wall in our free body diagram? What force, if we think of it from a car's perspective, what force, how does the wall impact the car? How does the wall exert a force on the car? What direction? Well, let's just say the car is going to the right. For a car crashing into a brick wall, moving to the right. So if the car is moving to the right, then the brick wall, right, the car is going to exert a force on the wall to the right. It means the wall is going to exert a force on the car to the left. This is a Newton's third law, an equal and opposite. Now it says label each force. We've done that. And finally it says, in what direction is the net force in the car? Well, again, simply looking at our diagram. Simply looking at our diagram, we know our normal force and our gravitational force are going to cancel each other out. Our car's not jumping up or sinking down. But our car is stopping. Our car is stopping, so we know there's going to be a force to the left And that's what the diagram shows us. There's an unbalanced force in our x direction, in our x-axis, and it's going to the left, opposite the direction of the movement of the car, right? The car was moving to the right, hits that wall, it stops. Well, that means there better be a force pushing it back the other direction to stop that acceleration. So the direction will be left. All right. Let's look at number 9. It says draw a free body diagram for the rock. Draw a free body diagram for our rocks. Again, what we're going to do, the first thing we're going to do is put our little square in here. Let's start putting in forces. Start putting in forces. All right, we're going to have gravity. So I'm going to just put force of gravity in here. How about our strings? How do we draw our strings on our free body diagram? How do we draw the force due to the strings on our free body diagram? Well, let's think of it this way. If you're holding something with a string, which direction can you move that object that's on a string? You can only move it along the direction the string is pointed, right? So we're going to have one force going up here. This is going to be a tension force, and we're going to have another tension force. Again, I'm trying to draw these parallel to the strings. I'm going to put it force tension left, force tension right, just to signify those. Now, what's the net force on our rock here? Everybody want to take a guess at this? What's the net force on our rock? Well, there is a force of gravity on our rock. You're right. Well, let's think of it this way. If the rock is hanging by these two ropes, is the rock moving? Is our rock moving? Can anybody tell me that? Right, correct. The rock is not moving. It's not moving. It's and we come back. We look at it a moment or two later. It's still not going to be moving. What's that tells us? It tells us our velocity is not changing. If our velocity is not changing, it tells us what? What does it tell you about your acceleration? Right, our acceleration is 0. So if our acceleration is 0, then Newton's second law tells us our net force must be 0. Okay, good, guys. Again, if you have questions, please type them in there as we go. This one's a rather involved question. This might take us the rest of the period. Let me see if there's one of the other ones I want to talk about real quick. I think I want to do one of these on the back page first, and then we'll come back to the force table one because it's a long enough one. I don't want to make sure I do a couple of these. So like these ones here. These are very similar to the ones we were doing in the simulations the last few days. So if we look at this problem 15, 2,200 kilogram elevator accelerates downward at 2.5 meters per second. What is the tension in the cable supporting it? So we're always going to start off with a free body diagram. We got gravity. Is there another force in this picture? Any other forces we should add to our free body diagram? Right, we got to put tension. And hopefully it makes sense. We're in an elevator. Our tension is going to be on the cable. That's going to be going up. So when we look at this problem, we've got our free body diagram in there. There's no friction. There's no air resistance. We don't have any other applied forces. There's not other than our tension force. So if we want to figure out the tension in our cable, remember there's two parts we've got to do here. The first one, we're going to look at our free body diagram. we got to figure out what our net force is from the free body diagram. So I'm just going to sit here and I'm going to write F net. Who can tell me what should go on the right side of our equal sign here? F net equals what? Tension, mass acceleration. Yeah, the mass acceleration, we're going to do that that's a second part of our problem. I don't want to do, I'm going to just strictly looking at our free body diagram here. F net, remember, that's a sum of our forces. We're going to add all our forces together. So what forces do we have in our diagram? We have our tension force. And we have our gravitational force. Should I add those or subtract it? Should we add or subtract the gravitational force here? Should we add or subtract the gravitational force? Well, let me try asking a question this way. Which direction is gravity which direction is our force of gravity pointing? It's pointing down. Is down our positive direction or our negative direction? Negative. So we're going to subtract our gravity. Our force of tension is positive, it's going up. Our force of gravity is going down, so we're going to make it negative. So when we sum all our forces together, we got our positive force of tension up, our negative force of gravity down. Okay. So this we got just from the free body diagram. Now we're going to come back where you were trying to go with me a moment ago, Abraham. Newton tells us that F net is equal to mass times acceleration. F net is equal to mass times acceleration. So we can put these two things together. These are the two steps I'm talking about. First one we get right from looking at the free body diagram. Second one we get from Newton. And if we put these together, what are we going to get? We're going to get Ft minus Fg is equal to mass times acceleration. So let's keep going with this a little bit. What does the problem tell us? The problem tells us that we have a downward acceleration. So if it's going downward, is our acceleration positive or negative? There we go. Awesome, guys. Negative. So we rewrite this equation here for our mass. We're going to put in our 2,200 kilograms. But for our acceleration, we're going to put in a negative 2.5 meters per second squared. Well, what's on the left-hand side of our equation still? We still have Ft. But we know what the force of gravity is here. I'm running out of room. We know what the force of gravity, we know Ft. We're looking for Ft, actually. We know what our force of gravity is. It's simply the mass of the elevator, 2,200 kilograms. And we're going to multiply that by gravity, right? Force of gravity. What's the acceleration due to gravity? 10 meters per second squared. Now, I want to be careful here. Oftentimes when I talk about gravity, I just go ahead and say it's a negative because I'm telling you about the direction. We've already included the direction when we wrote our equation up here at the top. That we have the minus signs here. We've already included our direction here. So I don't need to put a negative in front of that 10. We've already taken that into account. Okay. Let's finish writing on the right-hand side here again, 2,200 kilograms, negative 2.5 meters per second squared. So everything in here is a number, right? Except for our Ft, which is what we're looking for. We can rearrange this. We can use our geometry, our algebra to rearrange this. Right? We can say that Ft is going to be equal to what? We can take this negative 10 meters per second times our mass. Let's put it over there. It'd be a positive 10 meters per second times our mass. Positive 10 meters a second, negative 2.5 meters a second here. We're going to end up with 7.5 meters per second squared. Sometimes it doesn't quite respond the way I want it to. And our mass of 2,200 kilograms. Our mass of 2,200 kilograms. So we can punch that into a calculator. We can come up with what our tensional force is. Okay. Now, what I do want you to see, in addition to plugging it in, are we going to have a positive or a negative number here? Our force is going to be a positive number the way we've done our math. Let's take a second. Does that make sense? Is our force and of our tension in the positive direction? We look at our diagram, yes. Right? Our force is pulling up. Our cable is pulling us up. So we should expect our tension force to be a positive number. Okay. Let's see. Let's do... I'm going to do one more of these here. Let's do 18, and then I'm going to bounce back and do the force table. So woman catches a 0.12 kilogram cell phone. So let's put up our cell phone here. What are the forces acting on our cell phone? Got gravity. Now she's catching it. If the phone is falling and she's catching it, what direction is the force that she's exerting? Is it up or down? As far as the phone is concerned, right, she's exerting a force up. And she's slowing it down, so her force is going to be opposite of the direction of motion. So we have our free body diagram here. We can just go ahead and, from our free body diagram, write our equation. The force due to the woman minus the force of gravity. Again, the negative sign there because gravity's pointing down. So let's look at the rest of the problem. Somehow we want to use Newton's second law here. The problem doesn't tell us a force. It really doesn't. It doesn't tell us an acceleration directly, but we can figure out that acceleration. What do we have? Acceleration is delta v over delta t, right? What's our delta v here? What's our what's our final velocity? What's the final velocity of our cell phone here? Final velocity of our cell phone. Final velocity of our cell phone is 0. It stops. She brought it to rest. What was the initial velocity of our cell phone? It tells us 5.7 meters per second. How long did it take to do that? 0.4 seconds. So we can calculate our acceleration here. Negative 5.7 meters per second over 0.4 seconds. So I want you to see our acceleration here is negative. Acceleration here is negative. Oh, I'm sorry, positive, right? Because our initial velocity we have to subtract the initial, but our initial was a negative, minus a negative 5.7. The reason I want to do that, and this is a good check, I made the mistake here, what direction were we expecting our acceleration? She stopped it. So the object was falling down. She stops it. Our acceleration better be going up. If we do our geometry right and our math right, we're going to get a positive answer here. Remember, delta v is our final velocity minus our initial. Since it was falling downwards, our initial velocity was negative, so we're subtracting a negative. So we end up with a positive sign over there. 5.7 divided by 0.4. Let's do that really quickly on our calculator. Five 0.7 divided by 0.4. 14.25. Meters per second squared. Well, now we have our acceleration. We have our mass of our foam. So we can write our equation from Newton's second law. F net equals ma equals 0.12 kilograms times our acceleration, 14.25. Plug that into your calculator. Let me do this right here. Times 0.12. We get 1.71. Right, newtons. Remember, newtons uses kilograms. So we've got our from Newton's second law leads us to the conclusion that our net force is 1.71 newtons. Let's go back up to what our free body diagram told us. In our free body diagram, told us that not only is F net equal to 1.71, it's equal to our force from the woman minus the force of gravity. So we can do the force of the woman minus force of gravity is 1.71 newtons. What's our force of gravity? We know that it's mass times acceleration due to gravity. We're always going to use 10 meters per second squared for this class. Sometimes you'll see in the answer keys I use 9.8. That's close enough to 10. And for what we're doing, we're not doing any engineering here. I want to keep the math simple. So it's always just use 10 for the acceleration due to gravity. So what's this? This number here, this is going to give us 1.12 times 10. It's going to give you 1.2 newtons. So our force due to the woman is 1.71 plus 1.2, 2.92. Sorry, 2.91 newtons. Does anybody have any questions on this last one? This was a little bit involved, but I do want you to see there was nothing really tricky here. Just remember some of your base things. What did our free body diagram tell you? What does Newton's second law tell you? And this time we also had to use our definition of acceleration. Those three things, we're always going to use the two, free body diagram information and Newton's second law. Sometimes you might sprinkle in a few others. Well, seeing there's no questions, that's great. You guys should sound like you're going to be in great shape for tomorrow. Let's go back to the force table one, just because this is involved enough. I wanted to make sure I got through some of those other ones here. We've done this one a bit. Some of you did it with me, tried doing this at the lab with me right before Christmas break. Well, let's kind of go through our process. So we're saying we've got, let's do this one here. F1 is created by a bolt and a nut, 32 grams. 32 grams. So what's the force that bolt and the nut's going to give to us? It's mass times gravity. What's our mass here? We've got to convert it to kilograms. So we're going to say 0.032. Let me get my... Right, so our mass times mass times gravity here. Just for the sake of speed, I'm going to do it with the answer key I have written here that has the 9.1. So multiply those two together. That tells us what's our magnitude of force 1. We're going to do the same thing with force 2. Force 2 is created by a bolt, a nut, and 2 large washers. So it's 0.32 plus 18 from our 2 washers. That tells you that our mass here is 0.05. Multiply that by gravity. We're going to come up with our 0.491 newtons. We're going to use that equation a lot. Force equals mass times gravity when we're talking about a gravitational force. So then we got to break this down into components. We're going to break it into components. Now I want you to be careful. Look at how the problem is worded. Sometimes they're not worded really nice, and this is one case where it's not. It's telling us the angle with respect to the negative x-axis. The negative x-axis. We don't like that. That makes it very difficult to use. I mean, you have to keep track of a lot of things. So we're not going to do that. We're going to find, we want that angle with respect to the positive x-axis. So if the angle here, I'm just going to draw it on our wheel, if it's with negative 38, or if it's 38 above the negative x-axis, that's what it means here. It tells us that our arrow's here. But I don't want to measure it from the negative x-axis. I want to measure it from the positive x-axis. So how do we get this angle here? 180 minus 38. That's our angle there. We get here 142. So we're going to use that for the angle when we do our calculations. So in here we're going to take our magnitude, 0.314. We're going to multiply that by the cosine. Remember, x is our cosine of 142. If we're to get the y, we're going to take that same magnitude, 0.314. We're going to multiply it by the sine of 142. And we're going to do the same thing over here with our F2. For the purposes of time, I'm just going to skip past that right now. Then we have to add our vectors together. How do we add our vectors together? The x component of our sum is simply f1x plus f2x. We just add the two x components together. That gives us the x component of our vector sum. Similar with our y's. F1y plus F2y. Okay. Easy enough how to do our vector sums. Now, if we want to do the next part where it says the equilibrant, this is going to be the negative of our vector sum. Because we want it to cancel out, so it better be the other sign. So this is going to be negative Sx, negative Sy. I'm just using the variables here instead of the numbers, again, for the sake of speed. The solution key has numbers in here. What's our magnitude? Pythagorean theorem. Pythagorean theorem, we're going to take Sx squared, and we're going to sum Sy squared in there. We'll get our magnitude. Our direction, tangent to the -1, or inverse tangent, we're going to take Sy over Sx. Now, I want you to use a little bit of common sense here. If we're going to look at our diagram, if we know somehow we're canceling out a force that goes like this and a force that goes like this, hopefully it makes enough sense to you that your direction of your equilibrant force is going to be something like that, somewhere in there. So when we take this arctangent, your calculator is going to give you a positive number. Because our calculator for the tangent function, it's trying to put it into, I believe it's the first or fourth quadrant. Maybe it's first and second, depending on your calculator. So it's up to us to say, okay, wait a minute, calculator spat out an angle to us. We need to make sure that that angle is correctly into where it fits in our picture. So we might have to do a little bit of math to get the angle to be pointed in the right direction. Okay. That's what I want you to see here when you're doing this kind of problem. Oh, then finally, the mass necessary to make this magnitude. What's the mass? Let's take our equivalent force. So I'm just going to put EQ. And we're going to divide that by gravity. Gravity. Okay. Does anybody have any questions on what I just did here? Prashant, sometimes in the answer keys, I was doing them before. I did them with a 9.81 instead of a 10 for gravity. Right? For the purposes for what we're doing this year, I just want to make it simpler. So we're always going to use a 10 for the acceleration due to gravity, not the 9.81. In the answer key, I use 9.81. I got to go through and update it. I'll have the quiz posted tomorrow. I'm almost done with it. The quiz should be posted tomorrow by about the beginning of the school day, around 7:30ish. All right. Anybody else have any questions? Quiz is on exactly what we just covered today in this review sheet. Bye, guys. If you do have other questions, please just send me an email or set up a time we can talk tomorrow. Have a good one, everybody. Take care.